This is AP Calculus AB, and in this video I'm going to talk about section 5.1, which is extreme values of a function. This is the start of our next unit where we're going to get into applications of derivatives, and that's really what we're going to be doing for the rest of this semester. So as we go through this material today, you're going to find that for the most part this stuff is fairly simple and straightforward, but it is laying the foundation for a lot of more complicated things that we're going to be doing in the upcoming days and weeks. So to start with here, we're going to talk about this graph that I've included, which just gives you the idea of really what we're talking about today primarily, which is the idea of a minimum and a maximum, and then also what we call a local minimum or a local maximum, or an absolute minimum or an absolute maximum. Now, there is some interchangeable vocabulary here that you'll see from time to time, so I'll talk about that as I go through this. So first of all, when we talk about maximum and minimum values of a function, these are things that they're pretty intuitive in terms of looking at a graph and knowing when you're at a high point or at a low point. When we talk about a local maximum, we're just saying it's the highest point over some interval. And when we talk about an absolute maximum, we're saying it's the highest point in our entire interval. Same thing with a local minimum. If we're just looking at some small interval and we have a low point within that interval, we'd call it a local minimum. But if we're looking at our entire interval and we have a value that's lower than all the rest of them, that would be our absolute minimum. Okay, so like I said, intuitively, you can kind of tell what those are when you look at a graph. Now, the thing is, we have to be able to mathematically explain what we're seeing. And that's what these definitions are showing you. So when we talk about an absolute maximum or an absolute minimum, sometimes you're going to see those referred to as global maximums or global minimums. Those are interchangeable terms. But you can see when we have an absolute maximum, mathematically, the way we define that is, notice it says the function is less than some f of c value for all of the x's in our domain. So that f of c is the maximum if there's no points that are higher than it. That's essentially what that says. Now, same thing if I have a minimum. When I'm looking at a minimum, notice this time it says f of x is greater than or equal to f of c. So f of c doesn't have a point that's lower than it if it's going to be the absolute minimum. Okay, so then when we look at local max or local min, the term you'll see sometimes used for that is a relative maximum or a relative minimum. And again, those are interchangeable terms. But if I say something is a local maximum, that means that on some interval within my overall interval, I've got a point where there's a value f of c that's higher than all the rest of the function values. And then same thing with the minimum. On some smaller interval, I see that there's a point that is going to be less than all the other function values on that interval. So fairly simple for the most part. Now, as we go through these problems and as you go through your homework assignment, a lot of what you're going to do is just identify what these are in a graph. And so I want you to keep these definitions in mind, because when we start talking about how we actually evaluate these things, when we get to section 4.3, we're going to refer back to some of these definitions. So keep that in mind. Okay, so the other thing that I want to mention here is the idea of a critical point. So if you look at this graph, we have these points where we have the maximum and the minimum values occurring. So like for instance, here I've got a local maximum, here I've got a local minimum, here I've got an absolute maximum. But those are points where the function has what we call critical points. And what critical points are they are points within my interval, so they're not the endpoints, they're points within the interval where my derivative would either be equal to 0 or it would be undefined. You can see at this maximum point and this minimum point, we clearly have horizontal tangents. It looks like over at this point, we might have an undefined slope at that point because our left-hand, right-hand derivative look like they don't match up. There's that sharp turn in the graph. So those would all be considered critical points. These points at A and B are not considered critical points because they are endpoints. So just keep that in mind. So I'm going to talk about critical points as we go through this next part of this. So In your book, it primarily just focuses on the idea of finding maximum and minimum values from a graph in this section, but we're going to go a little bit further than that. We're going to talk about what's called the first derivative test. So the first derivative test is going to use that idea of a critical point that I was just mentioning, and we're going to use that to figure out how do we find a maximum or a minimum if we know where we have a critical point. And this is the way that it works. This is one of those things that once you understand it, it's very intuitive. It's sort of common sense, but now we have a way that we can describe and justify our answers when we see them. So the way that the first derivative test works is we always first find our critical points. And then what we're going to do is we're going to test around those critical points and see if our function changes direction at those points. So for example, this one where I have a minimum, you can see that my derivative was negative because my function was decreasing, and then the derivative became positive because my function was increasing. So that's how the first derivative test works. Here I've got a maximum. You can see the function goes from increasing to decreasing, and then sometimes what will happen is we won't have a sign change at those critical points, and these are referred to as shelf points. You can see that the function was increasing, hit a slope of 0, and then increased again, or decreased, hit a slope of 0, and then decreased again. So shelf points are not maximum or minimum points. They are something that we call a point of inflection, which we'll be talking about when we get to section 4.3. All right, so let's talk about how we actually do this first derivative test. So this first question says, use the first derivative test to find the relative extrema. So when we go through problems like this, we just have to keep in mind what exactly is happening with the first derivative test. So with the first derivative test, the first thing we need to do is we need to find our critical points. So I'm going to take my derivative, which in this case would be 3x squared minus 12, and I'm going to set that equal to 0. And so I can factor a 3 out. That would give me 3 times x squared minus 4 is equal to 0. And I'm going to end up with x is equal to plus or minus 2. Okay, so again, those are my critical points. And you don't have to write it out every time. I just want to make this really clear that these are my critical points. Okay, so now we're going to use something called a sign chart. And some of you may have seen these in pre-calculus before. There's different ways of doing sign charts. I'm going to show you the way that I typically do them. I try to do them in the simplest way possible. So in our sign chart, essentially what we're looking at is a number line. And on our number line, we're going to label our critical points. I'm also going to label on my sign chart that this is the sign chart for f prime. So this is going to tell me what's happening with f prime on these intervals. I know at the critical points, in this case, I have slopes that are 0. So what I want to try to figure out is what's happening in these 3 intervals that are created by those zeros that I have for the derivative. And so all I have to do is test points here. So for example, between -2 and 2, when I'm in that interval, an easy point to test would be 0. So if I plug 0 into this derivative, 3 times 0 squared minus 12 is going to give me a negative value. That means my function is decreasing on the interval between -2 and 2. Now, we can do the same thing on the other intervals. For example, when I'm to the right of 2, I could plug in a value of, let's say, 3 here. That would give me 3 squared would be 9. 9 times 3 minus 12. That's going to give me a positive value. Okay, so you can go through and you can test every interval if you want, but you can also use what you know about multiplicity when you solve these out. So I know if a root, which is essentially what these critical points are, they're the roots of the first derivative. I know if my multiplicity of those roots is 1, that I'm going to have a sign change at those points. Or if it's any odd number, I'm going to have a sign change at those points. If I have an even multiplicity, that means that if I were to think about the graph of my function would be bouncing off of the x-axis at those points. So both of these had a multiplicity of 1, so I know there's going to be a sign change there. So you can see my graph is now going from increasing to decreasing back to increasing. So I can go through now and I can figure out where do I have maximum and minimum values. And I don't usually graph this, but I'm going to show you this just so you can understand what my reasoning is. So underneath my sign chart, I'm just going to graph essentially what the function is doing. The function is increasing till we get to -2. It hits a slope of 0, then it decreases. Then it hits a slope of 0, and then it increases again. Okay, so obviously that's not what my function looks like exactly, but I know at this point, clearly there's a maximum, and this point, clearly there's a minimum. So I'm going to say there is a local maximum, and that would be at the point where x is -2, so I'm going to say that's at f of -2. So the function value, the original function, x cubed minus 12x minus 5, if I plug -2 into that, I'm going to get 11. We also know there's a local minimum at the point where x is equal to 2. So that would be at f of 2, and that would be equal to, let's see, if we plug that into the original function, we're going to get -21. Now, if I needed to justify my answer on this, I would just say there's a local maximum when x is -2 because the function went from increasing to decreasing at that point. Or I could say there's a local minimum at x is equal to 2 because the function went from decreasing to increasing at that point. So it's pretty easy to justify your answers, and this is one of those things that once you understand it, is very, very simple to do. So what I want you to do is I want you to try this next one. It's a little more complicated from a derivative standpoint, but conceptually it's the same thing. So I want you to take your derivative, get your critical points, and then test around your critical points and figure out where you have a maximum and a minimum. So I'll give you a couple of minutes to pause the video and then come back and I will show you the solutions. Okay, so here's what you should have ended up with on that one. You can see my derivative is a little messier this time, 2x e to the x plus x squared minus 3 e to the x equals 0. So I factored e to the x out, and it left me with a quadratic expression, which I then factored, and that allowed me to get these critical points. So when I got here, I'm just thinking about when are all of these different parts equal to 0. So remember when we were taking derivatives, and I kept saying, let's try to get these things into a factored form, this is really why. So e to the x is never 0. X plus 3 gives me -3, and x minus 1 gives me x equals 1. And then from there, you can see over here, I've created my sign chart. So again, I have a multiplicity of 1 on each one of those roots. So when I created this sign chart, all I did was use this middle interval, and between -3 and 1, I have 0 there. So then I just went back up to my derivative, and I actually used this form of the derivative, that factored form, because it's a little bit easier. I know e to the 0 is positive, and then x squared plus 2x minus 3 gives me a negative, so positive times negative gives me a negative. And then again, I know there's a sign change at both of those critical points because we had a multiplicity of 1. So based on that, I can see there's a maximum at -3, and there's a minimum at 1. Okay, notice I also gave the function values there. Sometimes on these problems, they're going to ask you to find just the x coordinate where there's a maximum or a minimum. If it ever says to find the value, that would be the function value. So be careful about the wording on those questions. All right, so let's go back over here to this next page. So that's really everything that's in this section from the standpoint of what you need to know. So like I said, when you go through your assignment in Math Excel, it's primarily going to be a bunch of graphs, and you're going to be looking where are their maximums, where are their minimums, and getting those really clear in your mind. What I included here as a supplemental worksheet is reinforcing the idea of the first derivative test. So this is not something that you have to turn in, but this is something that I really want you to work through. So I have this worksheet attached to the set of notes that just is titled Extreme Values, and it's going to have you go through a series of examples so that you really get a full understanding of where the maximum and the minimums are going to be occurring. Okay, so make sure you work through that. Make sure you work through the Math Excel. And next time during class, we'll talk a little bit about this worksheet. I will post the solutions for this worksheet in Schoology with the video so you can check your answers on your worksheet. But once you have graphed these functions on a calculator, it's pretty easy to verify your answers that you're getting without graphing on the calculator.